Good afternoon, everyone. Welcome to Taking It to the Next Level. I'm going to be talking about nested KVM on the POWER9 processor. So this slide sponsored by IBM Legal. So first of all, quick introduction. I live in Canberra, Australia. I work at AusLabs for IBM Australia. So we do a lot of Linux on Power. I work personally on the virtualization side. So that's both Linux KVM and qemu. So let's go into some quick terminology. First of all, what's KVM? Well, we're all here at KVM Forum, so I'm going to skip over that one. But let's go on to some nested KVM terminology. So we should be familiar with the idea of a host or hypervisor running on the bare metal system. I'm going to call this level 0 or L0. And then we have our guest, and I'm going to call this level 1 or L1. And now I'm going to introduce this idea of a nested guest. So now our first guest is a guest hypervisor, and then we have our level 2 or L2 guest running as our nested guest. So as you can see, we've got L0, L1, L2 increasing as we go down. Now here you're all saying, hasn't this been done before? I've definitely heard about this nested KVM thing. And yes, this feature is already present on x86, ARM, and S390. And in fact, already on PowerPC in the form of KVM-PR. So it's important to note there's two KVM modules on Power, both KVM-HV and KVM-PR. But before we get into that, it's important to note that there are three privilege levels on PowerPC. You have hypervisor mode, which is the most privileged, and where your host operating system runs. We then have the supervisor mode, or privileged, and that's where your guest operating system would run. And then the least privileged mode is problem state, or PR, and that's where your host and guest user spaces run. So back to this KVM-HV and PR. With KVM-HV, your guest is running in privileged or supervisor state, and then KVM-PR runs your guest operating system in problem state. So when I talk about nested KVM-PR, that's your level 1 guest in the supervisor state and level 2 guest in problem state. And level 1 has to emulate supervisor instructions for level 2. So I'm going to introduce this idea of nested KVM-HV, and that's what I'm going to be referring to as nested KVM for the rest of the talk. So you have level 0 using KVM-HV to run level 1, and level 1 then using KVM-HV again to run level 2. So now both your guests are running in supervisor mode and can use supervisor instructions. But level 0 might need to emulate hypervisor instructions for level 1. But why do you want to do this? Let's step back for a second. Well, the main reason is for testing. For example, OpenStack requires a large number of hardware configurations, and it's easier to do that in a virtualized rather than bare metal environment. It also means you can test hypervisor changes in a virtualized environment, you can test your hypervisor management software, and you can test migration of your hypervisors. Also, if you're already running virtualized, for example, you're in the cloud, it means now you can run KVM guest yourself. It's also a faster development process because it's faster to reboot a guest than it is a bare metal machine. And finally, because we could.
This is the most important reason.
So what do we need to make this happen? I talked about this nested KVM-HV thing, so running a KVM-HV guest inside another KVM-HV guest. So there's two things we need to do this. Once we're in the level 1 guest, how are we going to get into the level 2 guest? And then once we're there, how are we going to do level 2 guest address translation, so both instruction and data addresses? Well, before I get into that, let's very quickly look at what happens when we run a guest. So level 0 has the state of our level 1 guest saved in its memory, and it decides to schedule the guest at some point, and we take what I'm going to call the KVM entry path. So we load up the level 1 state onto our CPU, and we use this hrefid instruction to execute into our guest. Now at some point, an interrupt's going to come along that returns control into our level 0 hypervisor, and we're going to take what I call the KVM exit path, where the level 1 state is saved off the CPU back into memory. And now we're executing in our host again. It's important to note at this stage that, of course, level 0 is maintaining some page tables to manage the partitioning of its memory to the guest real address space. So that was the normal guest entry path. Now, how are we going to get into our nested guest? So like before, level 0 runs level 1, and level 1 decides to run its level 2 guest. And remember, level 1's in supervisor mode here. So it's going to use the same KVM entry path to try and load up its level 2 state, which involves accessing hypervisor SPRs and using hypervisor instructions, which are going to trap to level 0 and need to be emulated, hence why I've called this the trap and emulate approach. Now it's going to execute this HRFID instruction I introduced before, and level 0 knows that level 1's trying to enter its guest. So it can load up the level 2 state it saved away while emulating these instructions, and then use the same path again to get into our level 2 guest. And yay, we're executing our level 2 guest in supervisor mode. At some point, traps might return execution back to our level 0 hypervisor, and if we can handle these, we can go straight back into the level 2 guest. But eventually a trap's going to come along that needs handling in our level 1 guest. So level 1's going to use the same KVM exit path again now, which again is hypervisor registers and instructions it's going to execute, which will again trap to level 0 and need to be emulated. And eventually we'll get back into our level 1 guest, and at some point we'll go back to our level 0 host, and level 1 will need to wait to be scheduled again. So as you can see, there's actually a lot of context switches required between level 0 and level 1 on the entry path into level 2. So this is going to be slow, and it's just going to get worse the deeper that you nest. So here you're saying, there must be a better way, right? Can't we paravirtualize this with an H call? So I'm going to introduce this H call, H-enter nested, which level 1 makes to level 0 when it wants to run its guest. One of the arguments is the location in its memory of a level 2 state it would like run, and level 0 can load this onto the CPU and enter our level 2 guest. Just like before, an interrupt will come along that eventually needs handling in level 1. And so level 0 is going to write the level 2 state back into level 1 memory so that level 1 can access it and return from the H call. So how much is level 0 actually seeing here? How much state does it need to track for this level 2 guest? Like I said, most of level 2 state is actually just saved in level 1 memory. Well, each of these nested guests essentially becomes a shadow guest of the level 0 hypervisor, with some amount of state needed to be maintained. We need to know the level 1 LPID used for this guest. We need to allocate our own level 0 LPID. We need to maintain some shadow page tables, and we need to know where the level 2 process table is. Now don't mind if those don't make sense right now, I'll explain them in a second. So the first step I said was entering the nested guest, and we can do that. We can load up the nested guest context and then get into it. But on the very first instruction, we're going to take a page fault, right? How are we going to translate those instruction addresses? Well, before I go into nested guest address translation, let me very quickly explain how address translation works for a normal guest on the POWER9 processor. Well, it's a 2-level radix tree translation to get down to a hardware address. And we start off with this thing called a guest effective address, and this is analogous to what other architectures would call a virtual address. The first level of translation is called process scope translation, using radix trees in level 1 memory to divide its memory to its processes. It's associated with PID, and it results in a guest real address. The second level is called partition scope translation, and this uses radix trees in level 0 memory, and they're used to divide its memory among its partitions. This is associated with LPID now and results in a host real address or hardware address. So I've introduced a few concepts here that I'm just going to explain quite quickly. We have this guest effective address, which, like I've said, is just the same as a virtual address. We have a PID, which is a per process ID, used to tag cache entries and used for process scope translation. And we have this LPID, which is a per logical partition ID, again, used to tag cache entries, and there's one for each partition which will run on your system. The host has one, and it's normally 0. And there's also one for every guest. It could be 1, it could be 5, it could be 127. It just has to be a unique one for each guest. And that's used for partition scope translation. Now that might have been a bit hand-wavy, so let's go through a quick example of what the hardware does to get from effective to host real address. And I'm going to use an LPID of 7 and a PID of 0 here. They're just numbers I picked out of nowhere. So we have this partition table in level 0 memory with an entry per LPID. And each entry has a pointer to a partition scoped radix tree and a pointer to a process table in level 1 guest memory. We index that by LPID to select our partition table entry, and that gives us our process table. We then index that by PID, and that gives us our process table entry, which contains a pointer to our process scoped radix tree. And now we can do our process scope translation, which is just walking the radix tree, I'm sure we all know how that works, to get to a guest real address. It's always a two-level translation process, remember, so we still have to do partition scope translation. So again, we index by LPID and select our partition scope radix tree. And it's again just walking the radix tree to get to our host real address. Just a really quick recap. So we have our partition table, we index by LPID, and we find our process table. We index by PID, and we get our process scoped radix tree, and we do process scope translation. We then go back to our partition table, find our partition scoped radix tree, and do partition scope translation, and ta-da, we have our hardware address. Okay, so that was regular guest translation, but what about this nested address translation? That must be pretty easy, right? A few things to remember first. So level 0 has one of these partition table things in its memory, and it's used to set up mappings for the level 1 guest real address space. Now that level 1's going to run its own level 2 nested guests, it also sets up one of these partition table things in level 1 memory to set up mappings for the level 2 guest real address space. But there's only one register to tell the hardware where the partition table is. We could switch it, but we'd have to flush the entire cache every time. Also important to remember is each of these partition tables only does a single level of translation. The one in level 1 memory translates a level 2 guest real to level 1 guest real address. And the one in level 0 memory translates a level 1 guest real address into a level 0 host real address. But hardware needs a single mapping from level 2 guest real to level 0 host real address. So how are we going to achieve this? Well, what we do in level 0 is we allocate what is called a shadow LPID for the nested guest. And in this example, I'm using LPID 8. And then we go and we create an entry in the level 0 partition table for this nested guest, which will contain mappings for the nested guest. Remember, it's always a two-level translation process. So let's look first at process scoped. So the level 2 process table is in its memory and is managed by it directly. So level 0 can just copy this process table now. Okay, so initially it's stored in the level 1 partition table. So level 0 can go and copy that into its entry in its own partition table for that shadow LPID we've allocated for level 2. And now hardware can go and find this table and can do the process translation from effective to guest real address. Where it actually gets interesting is the partition scope translation. So we have this level 2 guest real address, which we found from the process scope translation, and we need to insert a hardware accessible mapping to translate that into a host real address. Hardware needs a single radix tree here. It can't just go and walk those two partition tables. But there's no reason software can't, right? So let's look what happens when we take a page fault on one of these guest real addresses and how we go and insert a mapping. So we start off with our level 2 guest real address. That's what we got from the page fault. And the translation for that into a level 1 guest real address is in the level 1 partition table. And so we just go and walk that in software. Of course, there's always a chance there won't be an entry, in which case we need to synthesize an interrupt to the level 1 operating system. And hopefully it will go and fault in an entry, and next time when we take the same fault, then we can find a translation. So let's imagine we found one, and now we have our level 1 guest real address. The translation for this into a host address is in the level 0 partition table. So we can just walk that again in software. Again, there might not be an entry, But since we're executing in level 0, we know how to create that mapping and can just go and fault one in ourselves. And so now we have the entire translation. So we have this shadow page table for our nested guests that we've created, and it's a combination of the two levels of partition scope translation. And it's in a place hardware can access now in our level 0 partition table. So what actually does hardware end up doing when we're translating a nested guest address? As always, we start off with this effective address. And as always, we go and look in our partition table, we find our process table, and we find our process scoped radix tree. We do our first level of translation, process scope translation, and then we go back, find our partition scoped radix tree, and do our second level of translation, partition scoped, and then we have our hardware address, which we can use to just go and fetch that memory. So a few points worth noting here. First of all, to hardware, all guests are the same. They will have a process table, which is in guest memory, which is associated with PID and does the effective to guest real address mapping. There's always our partition scope page table, which is in level 0 memory. It's associated with LPID, and it does the guest real to host real address mapping. And the level 0 shadow page table is really just the collapse of all the partition scope page tables in the levels below it. But each level can manage its own mappings now. So I was going to quickly talk about invalidation, but I might skip ahead, and if we have time, we'll come back to this. So you remember I said there were two things we needed to run a nested guest. First of all, we needed to get from a level 1 to a level 2 guest, and we introduced an H call to do this. Then we needed to be able to translate nested guest addresses, and so we have shadow page tables to do this in the host. Yay! So that's how we implemented it. Now let's go over some of the interesting features. First of all, nested. There's no reason level 2 can't run its own level 3 nested guest now. Level 1 will manage shadow page tables for level 3, just like level 0 did for level 2. Level 0 sees level 3 as just another guest of this level 1 VM. So now it's going to manage shadow page tables as well for that level 3 VM in the same way it did for level 2. Level 0 doesn't actually know whether level 3 is a guest of level 2 or just another guest of level 1. It doesn't actually see a difference. With this in mind, it's theoretically possible to nest indefinitely, given enough time that is, and memory, and maybe there's a few caveats. Another interesting feature is migration of nested guests. It's possible to migrate your level 1 guest, and all the nested guests just kind of come along for the ride. The state and memory of all the nested guests is in the level 1 memory, and that's the major part of the migration stream anyway. All of the state that's stored in level 0 can be generated or allocated again on the receiving side, except the location of the level 1 partition table in its memory, and so we just add that to the migration stream. You can migrate between levels. You can take your level 2 guest, migrate it up to a level 1 guest, migrate it back down to a level 2 guest. Why not? All these guests pretty much look the same. You just need some transport, of course, between your level 0 and level 1. So let's have a bit of a look at the performance. Was all this work actually worth it? What did we get out of it? So for a test, I ran a kernel compile with 40 threads and 20 gigs of memory. I used the P-series LE def config, and I ran make-j40-s. And this is a hot run just to make sure the page tables were already populated. And here we see a graph of the total time elapsed. You'll see going from host to level 1, we took about a 20-second hit, but there was only about 1 second slower when we went to the level 2 KVM-HV guest. Compare this to when I ran a KVM PR guest in level 2, and you'll see it was quite a big difference. I also ran a TCG guest, and it didn't go too well. Now the question on everyone's mind, but how deep can you go? Well, I ran a level 11 guest last week, again, because I could. And then I saw significant slowdown booting the level 12 guest. This is basically because the bouncing around of H calls just compounds as you go deeper. But if you can tell me a good reason why you need 11 guests, then sure. So what's the state of the code? So the KVM kernel patches are in the KVM next tree, so hopefully they'll make it into 420. And the qemu patches have been posted to the list, and will hopefully make it into 3.1 once the cap numbers are in the upstream kernel. So finally, how do you use it? So in level 0 on your kernel, you need to enable it as the module parameter. And then in level 0 qemu, you just set this cap nested HV equals true on your qemu command line. In level 1, in your kernel, you need the same patches you did in level 0, but there are no specific steps to take. And then for your level 1 qemu and level 2 kernel, there's nothing extra to do. It just works. So there we go. Now you can run your own nested KVM-HV guests. Thank you all for listening. Are there any questions?
So I actually have two questions. One question would be, you did that one test run with your page tables already fully populated.
Yep.
Do you have any numbers or graphs for the first kernel compile without page tables being populated?
I don't have any that I can display, but it was about 2 or 3 seconds more. So if we go back to this, so it was about 155, 156 seconds for the level 2. And again, it gets worse as you go deeper because of the bouncing around. So that's, yeah, when you're faulting in and having to create those shadow page table entries.
That's not bad. And the other question would be the part that you skipped. How do you actually do the invalidation, and how do you register the invalidation callbacks and stuff like that? Just a high-level overview would be interesting or sufficient for me.
Yeah, so really quickly, process tables are in level 2 memory. So level 2 manages them itself. That's not very interesting. What's interesting is partition tables. So first of all, level 1 could be invalidating a page that's mapped through to level 2. And we use an H call for that, which has level 2 guess real address. And we can just walk our shadow page table and invalidate a PT if we find one. The other case, of course, is level 0 invalidating one that's mapped through a level 2. And KVM code only gives us a level 1 guess real address here. So we can't go and find that. So what we do is we keep a thing called an R map or reverse map, which just stores the level 1 to level 2 guess real translation whenever we insert an entry into this page table. And then we can again use that to walk the tree and invalidate any PTs we might find.
So just to clarify, the H call is an hypercall? And
Yes.
is it a specific hypercall that you implemented or one that's available on the platform?
Yeah, so the instruction to invalidate partition scope PTEs is hypervisor privilege. So we could either have trapped on that instruction and emulated it, or instead we used an H call because we already used an H call for the entry path. And no, it's a PowerPC specific H call that was implemented.
Okay, so the 3 or 2 seconds you mentioned were actually with this special H call and not with the ordinary.
That's with the H call, yeah. I mean,
Okay.
It's pretty much the same as just trapping on the instruction and emulating it. Either way, I mean, the H call is just a trap to the hypervisor anyway. So.
Okay, thanks.
It was just nicer to use an H call because we already did for other things.
So we have some patches pending for nested word on ARM as well.
Yep.
And we also had to do the RMap
Yep.
trick, which x86 also had to do. Did you write separate code for that, re-implement what x86 had, or did you look at theirs and reuse it?
No, so that was a PowerPC specific implementation, but if we're all going to do this, I'm sure Christian would like it if we
Yeah, we should talk about that in the buff, because,
yeah, I wrote a for loop I'm particularly proud of.
we keep reinventing that wheel.
So.
Just a quick question. You mentioned Radix tree all over the place. Is it also possible to somehow use the old style hashed MMU guests?
Yeah, so currently this is only done for Radix, which was new in Power9. The idea would be, yes, eventually to be able to run at your bottom level hash guests. So you'd be Radix for the top levels and then hash for the bottom level. And that would just be a case of the same going in software, translating through the trees and then inserting it into a hash table for that bottom level guest.
Okay, thank you.
Thank you, everyone.